Hello and welcome to the Xapiens podcast. I'm your host, Lloyd Waits. I'm a physics student at MIT working in particle physics, nuclear medicine, and machine learning. Today I'm going to be interviewing Nobel Prize winner Frank Wilczek, who has not only won his Nobel Prize in asymptotic freedom, but has gone on to investigate the theoretical frameworks of particles like Axions and worked with groups that are expanding new technologies like quantum computing. Now, asymptotic freedom, for what he won his Nobel Prize for, is kind of a complicated concept, but it's at the core of understanding how our universe works and why we see things the way that we do in the terms of fundamental particles. Frank is a really interesting guy, and we had a great conversation about our lives, physics, and what we think the direction of the world is going to be in the next few years. So I hope you enjoy it. Thank you. So thank you very much for coming on today. We're super excited to have you. I read about asymptotic freedom in textbooks, so this is really
I'm getting old.
But so I mean, there's a long list of things that you've worked on, not just asymptotic freedom, which you won the Nobel Prize for. I have a list of them here, including being a professor at MIT. You're also the founding director of the T.D. Lee Institute and chief scientist at the Wilczek Quantum Center, Shanghai Jiao Tong University, a distinguished professor at Arizona State University, and a full-time professor at Stockholm University. Not only this, but you've worked with the Future of Life Institute with Max Tegmark, written letters with Stephen Hawking on the future of AI, and even worked with the United Nations. So
really?
there was I saw an article about you working with.
Not all those things have equal weight in terms of how much time I've spent on them. And you didn't even mention that I write a regular column for the Wall Street Journal.
Oh, well,
so,
okay.
And I probably bit off more than I can chew in recent years, and I haven't been able to spend as much time as I like on all these different aspects. But it's possible to. I think I've been able to do useful things. I tried to do the most. How should I say? Try to get the most bang for the buck in the time I put into these things. And fortunately, I get enormous amounts of help in pursuing different things in all these different forums.
Yeah. So, I mean, I know you say they have a lot of help, and you try and get the most bang for your buck. But how do you decide what's the best way to get that bang for your buck? How do you prioritize all these different things?
Well, it's a process. Every day I have an agenda every day for that day, and then once a week I revisit the agenda for the week, and once a month I do the agenda for the month, and once a year I do the agenda for the year. And sometimes, on long summer walks, I think about 5 years and 10 years ahead and what I want to be doing. So it's a constant process of adjusting priorities, seeing what's working, what's not working, So I don't only add things; I sometimes subtract things. and this pandemic era has been very significant that way, because I'm really thinking about what the best use of my time going forward is. For instance, it's become clear to me that schlepping around the world is not the great use of my time. so we want to do as much as possible remotely and do take it easy on my body and also just. I think people in general, not only me, but people in general, are reassessing what the importance of going to conferences, having meetings, all these things that you kind of been taken for granted as part of life, and really thinking about what's the value added.
So, I mean, kind of talking about this in a similar way, a lot of these task seems like a lot of administrative tasks and a lot of kind of going to meetings and talking to people.
Well, I think the only one that, of all these things, that's really involved a lot of administration has been the directorship at the T.D. Lee Institute, and that's been a kind of very special administration because, I mean, it's the word founding director there means that it's there are a lot of kind of policy decisions to be made that could be very important. I think the T.D. Lee Institute has the potential of being a very important resource for the physics community, opening up research opportunities for a very talented pool of people and a large pool of people, and an economy that's beginning to be able to support science in a big way and seems committed to doing that. So that I took on as kind of a service to the physics community, and for the rest, they really don't. I get a lot of help, and they don't involve a lot of administration. Thank goodness. The only thing that I have found burdensome occasionally is writing grant proposals, which is new to me. And when I first went to Sweden, I had to write a couple of very significant grant proposals to support myself, to make it possible for me to thrive there. But since then, things really have thrived, and now since I'm in that community and involved in projects in the community, I can get other people to write the grant proposals.
So with all these different tasks, do you still have time to do physics? Is that something that you're still
Oh, yes.
about? Okay,
well, I've had to change my style in recent years a bit. I used to be involved much more in the nitty-gritty detail of projects. And I still do that for a subset of projects where they're small, and/or I think I have a unique input. But in other projects, I've kind of systematically farmed out things that I thought other people could do to make them happen. So, I mean, notably, we'll get to this later probably, but notably, starting in Stockholm, we had a new idea for axion detection that seems very promising, did seem and very promising, but to really turn that from a bright idea into an actual physical experiment is, I learned, is a very big job, and it's been a lot of fun, but very different from anything I've ever done before, because it really involves working with a very large group, also not working with many aspects of it. And usually when I do theoretical projects, I'm at least aware of all aspects and feel that I understand them. But in this experiment, I certainly don't. I have a broad awareness of, but I wouldn't be able to do it, if you know what I mean. Making antennas and low noise amplifiers and metamaterials and so on. It's been fascinating to get a glimpse into that world, and it's marvelous to see the process where ideas get transformed into realities now. But now, of course, the proof of the pudding will be finding the particle. We'll see about that, but it's a very exciting process. I've really enjoyed that, and I wouldn't call it administration. It's really although it does involve working with people, it has a rich scientific and information content, but it's also very gratifying at a personal level to see other people taking up ideas and getting pleasure from them and working productively.
That's really interesting. So can you tell me a little bit more about Axions and kind of make the case? I've looked at Axions myself. Just kind of, I'd kind of like to hear from one of the major people in the field. What's the strongest case you think for looking for the Axion particle?
Okay, well, the so-called standard model or core theory has been just enormously successful. No clear discrepancy has been found from it, even though it makes very precise predictions for literally thousands of experiments, and people have designed to try to disprove it or push its limits, so it's been tested in very extreme conditions now, but there are a couple of things that are incompleteness of the theory or aesthetic flaws of the theory that are quite striking when you look at it deeply. So we should look at it deeply. It's close to the last word, I think, in physics. And one of the striking aesthetic flaws is that there's a parameter in the theory, something called the theta parameter, that a priori has a value between minus pi and pi. So it could be any within the theory. It's just a number in that range. But experimentally turns out to be, well, we haven't seen a deviation from 0, but it's certainly less than 10 to the minus 10. So that would be quite a coincidence if you just have a number that's otherwise unconstrained and it happens to be so small. So we suspect there's a principle involved, and the number has a very interesting qualitative meaning. Its most striking consequence, if it were not 0, is that it would give a new source of violation of. It would give a new source for violation of time reversal symmetry. So this amazing fact that the laws of physics, the basic laws, the microscopic fundamental laws, when you run them, if you run them backwards in time, have exactly the same form. So if you took a movie of a self-contained process, so we're not talking about big things where it's complicated because the second law of thermodynamics and so forth, but it's really small things where you can actually see the basic equations at work. If you take a movie of it and work it and run it backwards, it looks like a legitimate movie. You can't tell that it's been run backwards. Almost. There are some tiny obscure effects in the decays of elementary particles that are not quite that way. So it's really annoying explaining why it's not exactly a fundamental principle, but almost why. And we have a very complete story that would be completed if we could understand why that darn number, that theta parameter, as small as it is. That would really that would really tie up a beautiful story in physics where we now would understand why time reversal symmetry is almost but not quite realized in nature. So that, and then in the late 1970s, Roberto Peche and Helen Quinn put forward some ideas that could address this question. They introduced something called Peche-Quinn symmetry, and if you implement this symmetry, then it explains why this parameter is so small. It could explain. Now, that was very important work, but they failed to notice two things. that was where I come in. Well, I mean, actually, it's a little more complicated, but basically, because I didn't know about their work at first, but the two things they didn't notice are, first of all, that their proposal implies a potentially observable consequence and a dramatic one. It necessitates the existence of a very light, very weakly interacting particle. So, a particle with quite novel properties compared to the particles we know about, and so I realized that, and that's the axion. I named it the axion. There's a little story with that. I had wanted to name something axion, a particle an axion, for quite a while. I guess I was in my early 20s at that time, but when I was in college, I went shopping with my mother one time and noticed this detergent up on the shelves called Axion, and I said to myself, if I ever get a chance to name a particle, I'll name it Axion, because it sounds like a particle. It's really nice. It's like, it's like pion, muon, axion, and it's Greek, so it's Greek. It's ion, and so then when it turned out that this particle is connected to an axial symmetry, it turns out that really, so the stars were aligned, and I had a chance to name something axion. And it also cleans up a problem. So since the detergent, the stars were really aligned. Anyway, so I did. So pointing out the existence of this particle was one of the things that was missing, and then the other thing that was missing only really became clear 2 or 3 years later, which was the way the theory had been analyzed, both by Peche and Quinn and by me and by Steve Weinberg, who did similar work to what I did independently. By the way, he originally wanted to call the particle a Higglet. So I saved the world from Higglets, which is one of my great contributions, I feel. He graciously agreed to call it Axion. The other thing so the thing that we all did, which is kind of what people did at that time without much thinking about it, was minimize a potential. So assume that the world is in its lowest energy state. And when you do that when you minimize the potential, it's minimized at theta, very close to zero. And that's how the theory works. However, that's wrong. I mean, that's inadequate. Because the world does not simply, that's not the way the world works. It doesn't get a command from on high, minimize the potential. We understand the universe is a dynamic, has a history, a dynamics, and you really should work out the consequences of the equations in the context of that history. In particular, we now know a lot about physical cosmology. We didn't know so much then, but at that time, so that's one of the reasons why people did this default assumption, because they didn't know what else to do. But things were clarifying by the early 80s, and so I proposed that we should look at the cosmology of axions and how they get produced in the Big Bang, and so and then with John Preskill and Mark Wise, we analyzed that quantitatively and found a beautiful surprise that if you worked out how axions get produced in the early universe, they could solve a problem in cosmology that was emerging at that time, the so-called dark matter problem. Astronomers seemed to have built up a strong case that that they need a new particle that's very, very weakly interacting, and that forms a big fraction of the mass of the universe. In fact, it's roughly 6 times as much as the mass in conventional matter, like electrons and protons and the things we're made out of and the things you study in biology and all branches of engineering and chemistry. So axions, which were invented for a completely different purpose, just happen to also potentially provide the dark matter of the universe. And that's where we are today. We don't really know. We haven't yet. I mean, both the theory of axions in the sense of addressing this problem of why time reversal is approximately true but not exactly true, and the phenomenology of dark matter have really prospered in the intervening years. No competitive theory has emerged really in either case for the phenomena, and a wider range of phenomena has been studied, and all the theoretical arguments that we put forward have been very carefully vetted, and I don't think much is maybe tailored here and there a little bit, but really not changed much, and so there we are. So it's a very beautiful, or it's a very tantalizing situation that we have this convergence of different ideas that appear very solid, and now the task is to test them experimentally if we can. Axions have fairly well-defined properties up to one parameter. It's a one-parameter theory, basically. One parameter is still a lot, unfortunately, if you have to design different experiments for different values of the parameter, and the parameter can vary over several orders of magnitude, which is the situation. But people are rising to the occasion, and it's a very tantalizing process. It's also been very interesting from at a personal level, because for a long time, those of us who were Axion fans were kind of a voice in the wilderness. People thought the dark matter was something else, that these arguments were so recondite, so abstract and theoretical, and involved things like instantons and non-perturbative QCD, and the experimentalists didn't want to hear about that. They liked their WIMPs, and they were the much more kind of tangible particles that were more like the things they were used to, and but as time has gone on, and we've persisted in the evangelizing and very vigorous searches for WIMPs, both at the LHC and in astronomy, many different means, and specialized detectors that were very sensitive. They've all come up empty, though the window hasn't completely closed, but a lot of the glamour and hope of WIMPs in the early that people had has faded, and axions are now expanding to fill the void. Now, it's funny, if you look at the citations for the early papers, they kind of dribbled along at a few per year, and now it's like a hockey stick that's risen. Where it's depending on the paper, there are many papers now that have hundreds or thousands, close to 1,000 citations per year. Well, several hundred for sure, maybe and rising. So it's amazing. And I don't know how long that's sustainable without actually finding the particle that we can, and actually finding the particle that might go back down again eventually. But that's the situation now. It's very, very, very exciting.
I think it's interesting that you kind of consider yourself an outlier with working with Axions for a long time, because sometimes even when I give talks about Axions, people are still looking at me like, the soap? I have to explain.
Believe me, it used to be a lot worse. And, now there are regular international conferences, very well attended ones on Axions. As I said, but by physics standards, getting hundreds of citations per year for old papers is very rare. All right.
So there's a lot of talk about specifically the QCD axion, which you said. But there's also axion-like particle search, like a lot of the time with looking for specifically only a dark matter candidate that doesn't necessarily solve the Pesce-Quinn symmetry. How do you feel about those experiments? I've always thought that those seem a little bit odd to be looking for in a parameter space that is not specifically in the QCD axion space.
Well, it's less promising for sure, because it's lacking one of the main motivations for it. And when you have theoretical proposals that introduce more parameters than you need to fit, it's kind of weak. It's much better to have fewer parameters than I would say that the theory of axions is basically a one-parameter theory, but it's solving very serious problems all at once, and so so the so-called QCD axion is very well motivated. Let me put it this way: is a much better way to put it. We can put it shortly. In the case of the QCD axion, if you don't find it, that's also very interesting. That'll have a big impact. In the case of these other things, if you don't find it, well, okay, that's life goes on, no big deal. But I'm happy to lend the name to other things, because these particles do have certain commonalities with the axion, typically. I mean, and people, I find it touching that people want to tap into the glory, the reputational glory of axions to use it as a label for their proposals, but yeah, I'm just babbling at this point, but yeah, that's it. It's worth, definitely we don't know what the dark matter is. It may be more than one thing, and exploring new regions of parameter space that haven't been explored is, it's a spur to experiments, and you never, surprises might turn up. So it's I don't want to discourage that kind of activity, but it's not comparable in my mind to looking for the actual axion. Oh, maybe in this line I should mention one more thing that's not speculative and has been actually quite fruitful. You can look for elementary particles, new elementary particles that have something in common with the axion. But another direction is to look for realizations of the basic ideas and equations of axion theory, but with different interpretation of the symbols and different values of the numbers. To find what I'd call emergent axions in material systems, in condensed matter, and that's been very fruitful. Very pretty stuff has come out of that. So those are axion-like emergent particles that are quite real. This is not cosmological speculation, but real experiments on real materials. Something called topological insulators is highly related to the equations of axion physics. In fact, I wrote a paper called Two Applications of Axion Electrodynamics, which basically anticipated a lot of the main properties of topological insulators already many years before they were discovered and became popular. So it's been a fruitful thing to think about. And in general, one of the nice things about axions is because they're different, they've they've inspired a lot of creative thoughts that won't necessarily result in discovering the actual axion or be relevant to the original problems it was meant to address, but are of interest in themselves. And got new kinds of experimental techniques, new kinds of emergent particles in condensed matter, new kinds of materials that people are exploring. It's been really having a tough, well-motivated problem for people to work on is a great thing. Yeah.
Kind of like, what is elegance in each piece of equation? What would you say is kind of a fun question? What would you say is the most beautiful equation?
The most beautiful equation? Gosh, well, there's not a linear scale of beauty in equations. Different equations are beautiful in different ways. I mean, a standard one in that in mathematics that is is hard to compete with is e to the I pi plus 1 equals 0, because it brings in e, it brings in I, it brings in pi. And somehow from all these quantities that are not immediately obvious and have a long history, and people struggle to discover and even to accept in some cases, you put them all together in a very natural way and they turn out to be 1 or minus 1. So that's an extraordinary thing. So that's in pure mathematics. In physics, I guess if you had to talk about one equation, it would be the L equals square root of GR, where there's the equation that underlies the general theory of relativity. You can state it as I just did, in terms of a Lagrangian density. That's just almost laughably simple. And of course, that is not a true indication. As Feynman emphasized, you can put all the equations of the world into one equation, u equals 0, where u is the unworldliness. And you do things like the unworldliness of Newton's laws of motion is F minus ma squared. And you get the idea, you just keep adding everything up and put all of it equal to 0, and that has all the equations and is very elegant. You write it out. But this equation for general relativity is not like that. The symbols are very natural, and you unpack it, and all the information is there. It's not a fake. It's so that's very beautiful. But it's not different in kind from other beautiful equations like Maxwell's equations or the equations of the core theory. It's just maybe the most beautiful if you have to take one. Another very beautiful equation is. Just pick from a different subject, is it's not really even an equation, but there's a specific expression you can write down, Gödel's expression, that captures the incompleteness theorem. So it's a statement. It's in fact, it is an equation. It's an equation in arithmetic that when you spell it all out. But in the interpretation, it means that it's a statement that I cannot be proved, so it's a statement that if the logical system that it's expressed in is consistent, then it can't be proved, but it's true. so that's the essence of So that goes pretty deep. But probably the most beautiful equation is one we haven't found yet. That brings in even more ideas. And in a way, that's the goal of physics, which is of a certain kind of physics, is to make the ultimate description of the world more and more compact and have principles that, when you unfold them, have more and more consequences. We've tried to boil things down and boil them down and boil them down, and had remarkable success in doing that.
Yeah. So, kind of talking about these systems that can't be proved, or even emergent behavior that comes from very simple behaviors. Yeah. I've heard that you've begun foraying into a lot of biology, into some neuroscience.
Well, I've always been interested in neuroscience. In fact, when I was starting as an undergraduate, that's what I intended to study. I discovered that I really liked mathematics and did not like laboratory work. And so I kept looking, and at that time I didn't feel neuroscience, or was it, my ideas were quite vague, but it was something to do. I wanted to figure out how minds worked. So some bit of neuroscience, a bit of philosophy, a bit of mathematics, but I wanted to do. But anyway, the subject wasn't ripe, I felt, and so I looked around, and eventually, by kind of very contingent historical process, got into physics, and I'm not sorry. It's worked out pretty well. And I've really enjoyed it. But I've always kept contact with that stuff. So, and not just at a Scientific American level, but really, I'd say, with a little bit of preparation, I could probably pass general exam, to be able to launch into a PhD program at a serious university in neuroscience or other parts of biology. I've done a lot. I have done and continue to do a lot of reading there and thinking, but. I'm sorry, what was the original question? I kind of gone off.
Yeah, that's okay. Computational irreducibility.
I've gone off in these directions. So I just wanted to say this: it's not a new thing. It's not a sign of senility, or if so, it's been a long lasting process. But what's happened in the intervening years is that the subjects that I thought were not ripe, the possibility of understanding mind in a really profound way that's mathematically based and yet also reality based, has become much more imaginable. And the other thing that's changed is that I'm not a lowly undergraduate anymore, so I can command resources and get help and things. So yeah, I'm kind of interested in going back to those first loves, and I've been doing, kind of serious long-term investment in learning at a nitty-gritty level, especially about recent developments in machine learning, and as well as I keep up at the level of reading the news and views and things like that in Nature with what's going on in neuroscience. And the other thing, now that I'm a grown up and have some dignity or reputation, whatever you want to call it. I can call up leading figures in the field and get them to talk to me and get a sense of what's going on and what I should look into. Yeah.
Do you think that biological systems are computationally irreducible, or do you think that there should be some kind of analytical solution for a theory of mind?
Well, solution is too much, but I do think that there are profound organizing principles waiting to be discovered. I think, and the reason I think that is very concrete. It's in fact there are several reasons, but all related in spirit, which is that the difference between humans and which have clearly a level of mind that's interesting and qualitatively different from our apish ancestors at the genetic level is quite small. And so there has to be some parameter you can dial just a little bit to get from them to us. And also the architecture of the brain contains many repetitions of a kind of simple design. With 6 layers and mini columns and things like this. So, and in some ways, the most salient difference between or a salient difference, and probably at some level, the salient difference between the apes, which have certainly a relatively primitive mind, and humans that have a much richer mind, is that our brains are bigger. They just have more copies of these things. And so the great principle of how you use many copies to do more stuff, I feel might be quite deep and profound, but not complicated. That's once you find it. And it also points in interesting directions. And by the way, that's kind of, it's not unrelated to what people have discovered in neural nets, which is that it was the same, the basic ideas were already in place in the 1980s. And with a little broader conception of what the basic ideas are, they go back even further than that. What made the difference is just having not enough processing power and enough information gathering power. Not in humans, of course, we gather information by vision and things like that. But computers at present don't do that. But you just give them the information in a form they can understand, and they digest it. And that's been using neural nets, which were inspired by the brain. Of course, they're very different in detail, but at some level, probably have quite a bit in common in principles. So anyway, I'm kind of rambling, but the idea is that I think there is a great opportunity there to find an organizing principle, and there have been deep discoveries in biology that have a lot of universality. Certainly, in the whole story of molecular biology, the prominence of DNA and RNA as a messenger and things like this, and the cell cycle now is also very much elucidated, and metabolism is very much elucidated. Metabolism is kind of ugly, but all right, that took a long time to evolve, so maybe that's harder, probably. So there are sort of existence proofs for great organizing principles that aren't that complicated in biology. Now, there are certainly many things that are contingent too, Why do we have 5 fingers and not 4 or 6? Probably contingent, and why why we know for sure why the land on Earth is not ruled by dinosaurs was highly contingent, and things might have been quite different, except that an asteroid or meteor crashed into the Earth, and so now we just have birds, not that. Anyway, so I don't think there'll be a theory of everything in biology. For that matter, I don't really think there's a theory of everything in physics, or ever will be. But but there can be great generalizations, and I think at least one great generalization is yet to come.
So that's interesting. I feel like it's not very common for, I don't know if I've ever heard a theorist say that I don't think there's going to be a single unified theory or a theory of everything, because I feel like that's kind of the ultimate goal that so many of us have marched for so long.
Well, maybe it's, I think, partly a matter of semantics. I like much better than a theory of everything. I liked Steve Weinberg's phrase, which is a final theory. So now, a final theory, if you think about what a final theory means, it means that you stop looking for a better theory. So that could happen in different ways. The optimistic way is that you find a theoretical framework that is beautiful in some tangible way, in some widely perceived way, that's very difficult to change without wrecking it. And that explains a lot about how the world works when you spell it out. That I think is possible. It's possible we'll get there. We've gotten a long, long way along that road already, remarkably. If you think about the kinds of speculations that the ancient Greek philosophers had, or even that Isaac Newton had, or even James Clerk Maxwell has, things have come a long, long way. Or even Einstein. He had vague ideas about a unified theory, but now we've really made big steps in that direction with numbers and facts, and I think it's conceivable we'll reach a final theory in that sense. It may even be that string theory will be a final theory in that sense. I hasten to add that it's not there yet by any means. No one has derived even a single significant empirical consequence from it. So, or demonstrated at any but the most hand-waving level how it could give the parts of physics we already know about. So I don't accept that it's even a candidate theory. It hasn't earned the status of candidate theory of everything yet, but it might. And that's the optimistic way. Is that, or I shouldn't say theory of everything. Final theory, theory of everything. We'll come back to it. That'll never happen. The pessimistic scenario is that you'll have a final theory because people just, we have a really, really good theory that explains a lot. And that people just, but not everything. There are loose ends here and there. It's not as beautiful as it could be, but it just gets, people get tired of it. They are trying to improve it because it already covers a vast range of phenomena. The phenomena that it might not explain, you have to go to very extreme conditions to set up, like bigger and bigger accelerators, and people say, "Oh, it's just not worth the money. It's not worth the time. Who cares?" I mean, that's another way you could have a final theory, and that's also, I'm afraid, not unrealistic. That things could happen that way. Okay, but in any case, a final theory, I think, could happen, and we may even be approaching it by either one of those two routes. It won't be a theory of everything if you could achieve that. Clearly, it's not a theory of everything. It's not a theory of love or human harmony or war or bring it a little more down to earth. It's not a theory of how you make minds, how minds work. Very, very striking phenomena in the world that we'd like to would not be even advanced, let alone solved by so-called theory of everything. It's not a theory of everything. It's a very, very specialized aspiration to get a theory that people either don't think they can improve or don't care about improving.
So we talked about with biology how a lot of it is just kind of stacks of copies on top of one another over and over again. And we've also talked about how kind of in the standard model, it's difficult to take all of these fundamental ideas and say, I don't know, lead-lead collisions isn't going to be easily predicted by the standard model. It's a much more emergent behavior. Do you think that there's something kind of that these two could grow together? I know there's been a rise in computational physics theories where you have this idea of taking multiple stacks and stacks of some kind of simple rule or some kind of basic physics principle, and then using that as a kind of way to build up a final theory or unified theory.
Well, it's conceivable, I guess, that we'll have a final theory that looks very, very different from the kinds of theories that have been so successful in physics so far. Things like that have happened in the past, of course. We had extraordinarily successful framework from Newton of particles and forces between particles that was, predicted many, many things quantitatively with extreme success, but then started to show seams in the 19th century and gave way to field theory, which has introduced a host of new ideas, none of which were, I would say, in conflict with the Newtonian framework, but certainly required additions. And that was very successful, electromagnetism and everything. But then that got replaced by quite a different theory that's really profoundly different. I mean, well, first of all, there's the relativity theories, which I would say are not profoundly different. They really are in the spirit of field theory of electromagnetism. They introduce a host of new ideas, but I wouldn't say they required to unlearn anything, really. Whereas quantum mechanics really was very profoundly different. And it's amazing that you can have such a successful theory as pre-quantum physics that explains so much that is profoundly misguided in some sense, right? As the real story, when you go one level deeper, is quite different, and in fact, it's a very challenging problem that people are still working on to show how classical physics and the classical world emerges from the quantum world, which we think is more accurate. And so based on all that, it's conceivable to me that the present formulation of physics, which is based on continuum, space-time, and real numbers and quantum fields and all this stuff, that would be replaced by something different, something that's more digital, like a cellular automata or something. It's conceivable, but boy, it's a tough thing to let me put it this way: it's not conceivable by me. I don't know how to do that. And I played with it, tried to give it a chance, but it's not easy, because even to do basic things like implement conservation laws, implement symmetries, which have been profoundly fruitful guiding principles in getting to our understanding in physics, and are embedded in our best models of the world. You have to sweat blood and tears to get them, and it looks very ugly to implement them in these other frameworks. So seems tough. but there might be but like in the case of quantum mechanics, it didn't discard classical physics. It you still have P's and Q's, momenta and positions, but they just don't commute. So, well, you have but you also have a different framework. You have Hilbert space, and if a sufficiently profound modification might involve a synthesis of different ideas. So, for instance, specifically, an idea that I have a lot of sympathy for is that there's an atomic structure to space-time. That space-time itself is made out of some kind of particle, roughly speaking. But then you have to say, what are the laws for those particles? And I think those laws, it's very hard for me to imagine that they will resemble the laws of simple computer programs for cellular automata. They're much more likely to obey a different set of ideas that are more related to quantum mechanics as we know it.
So what would you say are some of the most promising areas of physics then?
Well, in fundamental physics, in the sense of discovering new laws and things that aren't implicit in the laws we already know at some level, I think Axions and dark matter. I also think we have very compelling numerical evidence based on unification of couplings that there should be supersymmetry in the basic principles of physics. Unfortunately, some people jumped the gun and said that supersymmetry has to show up at the LHC. The real quantitative evidence from unification of couplings, unfortunately, is on a logarithmic scale. So it's very difficult to say that the scale should be 1 TeV versus 100 TeV. The calculations will still happily accommodate supersymmetry at a higher scale, slightly higher scale, which is easy for theorists to write down, but very difficult to access, very expensive to access experimentally. So, but okay, and in a similar vein, proton decay. Our best ideas about unification certainly point to the instability of protons at levels not so different from the current limits. So, in fact, I expected proton decay to be discovered quite a while ago. It hasn't been. But again, it's one of these things where, unfortunately, a small difference in the theoretical calculations can make a big difference experimentally. Because in that case, it goes like the fourth power of the unification scale, and so and also in other models, it depends on the details of how supersymmetry is broken, and so we don't. But it's very, very difficult to push the theoretical predictions far beyond the current experimental limits. So I think that's an important direction to look at for fundamental physics. And then there are purely theoretical things, and that's harder without the discipline. So it's harder to put your finger on what the point is, or what. So I'm not going to. I wish my string theory friends good luck, but I don't. I can't point to anything specific that should be the focus there. But to me, there are other kinds of physics. You might call them emergent physics or applied physics, depending on your mood, or that present extraordinary opportunities that have really been revolutionized by the power of computers to do numerical experiments, if you like, and then so you can have wild ideas and test them numerically, and then hopefully also test them in the real world once you refine them, and that's kind of a two-way street. On the one hand, physics can suggest new technologies. In particular, I think maybe the most vibrant area, but there are many vibrant areas, but maybe the most vibrant area that's on a broad front is people are becoming much more sophisticated about using deep principles of quantum mechanics to design new kinds of sensors that exploit things like tunneling and coherence and entanglement to make more refined kind of sensors, new kinds of instruments that allow you to see things that you couldn't see before, or didn't even think about before, but the technology poses questions of how you probe entanglement and things like that. Technology can drive physics, and physics can drive technology, and in the case of computation, as I mentioned, computation allows you to do numerical experiments in the broad sense, including trying to build protons from pure numbers, and that's actually been quite successful, extraordinarily successful. I didn't see that coming, even though I was instrumental in getting the equations to see them solved in that way. It's just came as a complete surprise to me, and but the whole world of chemistry and lies open in principle. We know what the equations are.
Mm-hmm.
Compute, do it.
Go.
Right, and and the world is waiting for new materials, new catalysts, new drugs, all kinds of new things. Okay. So here you've got the equation. Let's do it. Right. So that's an extraordinary thing, and it could be that we need quantum computers to do that. Computers that really use the deep principles of quantum mechanics, and it's very exciting. We could be facing a very different material world in 20 or 50 years, thanks to these developments. And it's intellectually rich also. I mean, of course, what I know the most about and what I'm most pleased with is the parts that I participated in, and it's been a real thrill to see anyons discovered in a clear way in the last couple of years, and start to become a useful tool possibly for technology. There's a whole field of topological quantum computing that is based on anyon, but then there are also the underlying ideas have played a very important role in setting up what's called toric codes and schemes for error correction that we'll really need in quantum computers, unless the topological quantum computation really works, then you won't need the error correction. But if the toric codes are kind of a way of getting topological computation without having the anyons, but the anyon ideas are still what drives it. So that's I'm really happy with that. And it's it started as a complete just curiosity about originally about cosmic strings and their properties, but then take a slice of it, you get two-dimensional materials and odd properties that really have a striking appeal to a physicist, to a theoretical physicist, because they overthrow conventional wisdom. People thought you could have only bosons and fermions for a long, long time, and the idea that there are other possibilities was quite entertaining. And then again, it's come really as a complete surprise to me that they might have some use. Well, not a complete. I mean, a surprise, not a shock. I mean, anything that's buildable at a reasonable price could have some use, but I certainly didn't have the concept that they could be used for information processing, and or even initially that they could be realized in actual materials, but that came pretty quickly.
Yeah, it's funny that you mentioned these new types of materials and kind of deep use of quantum mechanics, because on another one of our episodes we actually had someone, Deblina Sakar, who works in neuroscience, developing sensors that take advantage of quantum mechanical tunneling and using that for new types of neuroscience sensors. So that's kind of exciting. I also need to say, as someone who designs a lot of the magnets, I wouldn't describe supersymmetry as a low hanging fruit by any means.
Did I talk about? Did I? No. Of course not. I mean, you have to. Not only the magnets, but the whole enterprise of big accelerators is extraordinary. Right. Extraordinary convergence of all kinds of insights into the world physics, ranging from magnet design to detector design with fast electronics and vast amounts of computation to analyze the results, some of which uses neural nets. So yeah, I mean, it's our civilization's answer to the pyramids, but much better, because it's
more useful than a big pyramid in our backyard.
It's driven by more laudable goals, I think, and also it's not. Well, it involves graduate students, but not slave labor as such.
But I guess my point is that with supersymmetry being so difficult, but you were also talking about how in biology and these are all ripe for the taking. Do you think there's any kind of like very ripe low hanging fruit left in physics, or do you think we're
I see what you mean by so it depends what you mean by low hanging. So there are ideas that seem very ripe, so very ripe fruit. Now, low hanging is, I guess, it depends on how big a ladder you give yourself. But what I took to be low hanging is things that we sort of know how to get to, and it's just a matter of expense or dedication. The really low hanging fruit, I guess the model is that some lone genius in a loft somewhere has a bright idea, and people say, "Oh my gosh, how did I not think of that?" And do the experiment the next day, or maybe the person does the experiment himself, or doesn't need an experiment. It's just so obviously true, and things like that can happen. I would say, something like that happened with inflation. There's a really great idea that wasn't there one day and was there the next day, and in retrospect, the basic, everything you needed was there. I regret to this day that I didn't think of it, but so it can happen. It's very difficult to anticipate, because low-hanging fruit these days, with so many physicists around the world and bright people, doesn't usually doesn't go unpicked for very long. And if I knew something like that, I wouldn't be telling you. I'd be doing it, But but I can tell you that there's the first category of low hanging fruit is where you a much more inclusive definition, which is at least you know how to do it. And so the other kind of the unpredictable low hanging fruit that might be low in the sense that a single person could grab it in one go is very difficult to know in advance. Clearly, it gets harder and harder as our sophistication increases. But even in fundamental physics, for instance, I mean, famously or infamously, string theory, which is a very serious enterprise and may well contain the ideas that will lead to a final theory, doesn't really have a formulation. It's called a theory, as if there's a theory, but it's not. It's really a grab bag of ideas that have a certain inner coherence, but I don't know what the question is to which string theory is the answer. It doesn't have anything comparable to gauge symmetry or the principles of general covariance and general relativity, or even things like chirality or something. It doesn't have a leading principle that organized, and you can't write down what the equation is. There's no equation to which it's the solution. So maybe some bright person will figure out what the missing principle is, and then this grab bag of ideas, maybe transformed in some way, maybe added to, suddenly will become much more usable and much more predictive, and so it's conceivable, but it's been a while, and that hasn't happened, and so it can't be too easy. Well, I don't know. I mean, it's hard to tell. It's hard.
So, do you think a good theory has to fit on a T-shirt like the standard model compared to kind of being a grab bag?
No, not necessarily. But that's historically that's often been the product of this process of trying to boil things down and get the logical principles clear, and in physics, that's certainly been the ideal for a long, long time, and has been a very fruitful ideal. But the world doesn't necessarily have to cooperate. There could be things you could have. Well, a thought experiment that I often regress to is I think it's very plausible that you could, and maybe someday, thousands of years from now, people will be able to create worlds inside computers that contain intelligences that don't know necessarily that they're inside a computer, or don't think about themselves that way, but these entities would live in a world whose laws are programmed, right? They not given by God or Plato or whatever, that as in the form of elegant equations that involve continua, and so but as a program that somebody wrote, and they could look very inelegant. They could look, most programs are inelegant. They have to deal with all kinds of contingencies and exceptions and things, and then, if such an entity tried to figure out the laws of their world, they would not be able to find a concise description. They would find more and more things, that different laws apply to different levels of the game. If it's a Super Mario world, but each one has its laws, but there's no way of getting unified description, really, except by making a really fanciful theory that maybe we're inside a computer and there's these guys who obey the laws of general relativity and quantum mechanics and they've programmed us. But that would be a highly speculative theory, and a kind of useless one, right?
So, I mean, I guess kind of the obvious question from that is, do you ever feel that way with us? That
no, no. I thought. I know. That's been a popular
science
idea or
trope.
joke or something. Some people pretend to believe in it. I don't know if they. It's so. But it's interesting enough to be taken seriously. But I think if you take it seriously, it kind of doesn't really hold up very well. Because the two. Well, first of all, there's the zeroth order question. Okay, if we are. If the world as we see it, as we experience it, I'm of course going to trust that I experience things roughly in the same way as you do. That it's all an illusion, that we're really inside a computer and just seeing electronic input from something. It begs the whole question of what's the computer made out of, and then there's internal evidence that, to implement the way the world works according to our understanding of basic physics, you use continua, you use a lot of hidden complexity. A proton is actually a very complex object, and yet you choose to build human beings out of that. That's very poor programming practice to build in all this complexity that you don't use at all, and also there are many opportunities. If you're doing a computer program, there's no reason to make the laws local. There's no reason to forbid time travel, and so there are many things you could be much more creative than the very constraining laws of physics we have. So I just don't think it's at all plausible.
I do like the image of a computer programmer writing down all of these laws, and then someone saying, "Oh, I accidentally set theta to 0. And now they're looking for an axion. What have I done?" I've thought about this question before too, and I've always kind of thought, does it really matter? Does it matter if the equations were written by God or by Steve, the computer programmer, at his house, and just kind of made us? Because it's still, it wouldn't really make a difference to me.
Well, if you believe in the computer metaphor, it suggests questions that then you can address experimentally. Computers, we know. The problem is that the most obvious experiments show you the idea is wrong. You would not expect the laws, in such a realization, you would not expect the laws to be based on continua. You would not expect them to have a lot of hidden complexity. But there are other things you could look for. You could look for, you would not. I could go on about things you would not expect, but the that we do see. But you could also look for things that are characteristic of computers, like maybe there's a transistor that blew, and so you get errors. Where are the errors?
I don't know. I feel like I've been in some errors sometimes.
Do you see a pixel somewhere that's not functioning?
Okay. I mean, that's true. But I mean, to play devil's advocate, you could always say like, "Oh, these are what all these ghost sightings are." That's what all these ghost sightings are, or UFOs. Or, they're all just glitches in the matrix.
Okay.
But,
yeah. Sure.
But anyway, so I mean, in all these cases, physics is obviously a very important part of your life. Why is science so important to you? Was there something when you were growing up, or did it just kind of you just thought it was cool and did it?
Well, some combination of those two. I think I've had a very natural propensity towards thinking logically and also thinking big about what does it all mean, and trying to make big numbers and think logically and solve puzzles. I always have loved solving puzzles and still do. And but it also, I think, that kind of propensity was very much nurtured by my parents and the society I found myself embedded in as a child. I grew up during the Cold War, when people thought, I think was widely thought, but also by people with power, was thought that the future of the country, the security of the country, depended on science and training young people to make new kinds of devices, new kinds of bombs, and space vehicles, and all kinds of things. And so it was very much encouraged in school, and then. And I went to great universities. I went to the University of Chicago and Princeton, and there was a thriving scientific culture into which I could easily fit, and that's what happened. So.
I heard one story about, I think it was after World War II, where there was a bus of physics graduate students, and they stopped at a diner, and they all said, "Oh, you guys are nuclear physicists. Let's buy you lunch. You saved the war." And
right,
was kind of like, sure, I'll take the free lunch. But it's not like I was on the Manhattan Project.
Right.
I always thought that was very funny in that time. But so say you had this kind of limitless amount of funding, for example, and you were kind of given the job to prioritize each of these different projects that you're interested in. How do you think you would spend all of this funding? How do you think you would prioritize and reorganize?
Well, infinity is a very large number.
Well, let's say arbitrarily large, but not infinite.
Well, in the case of Axion searches, proton decay, exoplanets is another one that we didn't mention, but is very, very, very interesting. These are not limitless projects. I mean, let me put it this way: you could do a lot with a very finite fraction of the available wealth of the United States. I think, if I remember correctly, our gross national product every year is $22 trillion, something like that. I don't think it would be crazy to invest $1 trillion each year, and that would be ample to fund, I think, those initiatives more than adequately. In fact, it wouldn't require anywhere near that amount. So now, if you want to build gigantic new accelerators, it could get serious. But even then, they're much less than $1 trillion over several years. So you just got to So I think the answer is all of the above. should do all of them, and you should also spend more on science education and make sure that the young people who could be contributing and would like to contribute, or who would just like to appreciate and be able to have the fun of understanding what's going on, that they should be brought to a level where they can do that, have the opportunity. So the scientific experiments. There's also investing in improving the internet and communications, so as to enable that kind of worldwide educational process. But of course, just building the infrastructure is not enough. You also have to train teachers and develop teaching tools to make that happen. So, yeah, with $1 trillion a year, I could do a lot. Not that I'm volunteering to administer, but that we could change the world in a very, very positive way with that kind of investment. And I don't think it's a crazy thing to be asked to ask. I know it's politically completely impossible in the present situation, but if wiser people were in charge, and the value of long-term investments were appreciated, I think that would be a very wise one.
So on the topic of education, a lot of people will typically say, like, "Oh, I hate math. I didn't know math when I was in grade school, and it's kind of a problem." But a lot of the talks I've seen you give describe math using pieces of art and describing symmetries. Do you think that there should be kind of a different way to teach math for a lot of people?
I do. I mean, I have some concrete ideas about that, which may be wacky. I'm certainly not an authority on education. I know, but a lot of people like math without knowing it. Not knowing that they like it, because they think of math as arithmetic or algebra, and they got confused in the early stages of algebra and sort of never recovered. But if you go to the supermarket and look at the kinds of magazines they sell, well, they sell a lot of hidden word problems. That's not mathematics, but they also sell these books of logic puzzles that really are mathematics. There's hidden mathematics, they can be quite challenging. Actually, it's very impressive. So people do this for fun, right? So I think there should be much more stress on logic puzzles and things like that in math training that don't necessarily even involve numbers, but involve working with concepts. And I think it would be very good to teach logic, both formal and informal logic, as opposed to, say, trigonometry. Not that there's anything wrong with trigonometry, but maybe in the modern world, the priority, and to be more inclusive, I think there should be other priorities. And another in the realm of geometry, one of the little joys of my adult life has been learning about how projective geometry is used in art to draw things. Because I'm truly horrible at drawing. It's unbelievably bad at drawing. But with the help of basic ideas of perspective and making grids and so forth, which is a really relaxing, nice activity. You can draw things that are quite striking, and I mean I can, and that, I think, instead of teaching Euclidean geometry the way Euclid did, I think it would be a really good thing to do projective geometry and integrate that with the study of art, because it's historically it was a tremendous thing in art when that was developed, what was first developed in the Renaissance, and so you could be learning about that and as well, learning the techniques and producing beautiful objects all at the same time, and so and then another place where I think there could be innovation is teaching more about symmetry from the very beginning. So, yeah, I think the mathematics curriculum kind of got ossified, but I think more logic, more symmetry, more art, specifically projective geometry, would really bring more people in and get them excited, and then they can fill in the trigonometry. Yeah. Right.
So I mean,
so in other words, I guess the overriding theme is to make things more concrete, not to demand at the very beginning levels of abstraction that kind of can discourage people if they don't get it, or just leave people cold, because who cares about this? Who cares about solving abstract equations between symbols? All right.
But so I mean, I think that's interesting because so many people consider art and math and physics so completely separate. But
no, they haven't. Well, historically, they certainly haven't been.
Mm-hmm.
Projective geometry came out of the needs of artists and making perspective. And for instance, some developments in optics were also spurred by artists and artistic needs. And photography, of course. There are many examples where what you could call it science or you could call it art, but where the opportunities opened by technology have led to new kinds of artistic expressions and vice versa. Electronic music. I think there are lots of opportunities too, now being opened up by our better control of the world.
So, I mean, a lot of people, when they do art, is usually considered something heartfelt, something that they're trying to communicate. Where do you think that line is between doing a proof using projective geometry and having some kind of actual heartfelt message thrown as
well, art? It doesn't hurt the feelings of your heart to draw things that look like the actual world. So these are enhancements. They're not constraints. I mean,
more tools to use.
They're tools to use. Yeah, exactly right. Ways
in kind of a similar vein, what do you say about something like literature? I mean, GTP3 can only take us so far in kind of writing books.
Well, but there's going to be GTP4. Yeah,
1 trillion free parameters.
Well, I'm not sure what the question is. Literature is good.
I mean, if GTP4 writes a novel, do you think that you would be able to enjoy that novel as much as one written by a human?
Well, not as GTP3 is now, for sure. But I mean, the best human novelists are far better than any artificial production. But I do think, if you step down from the highest expressions of art to expositions, manuals, I think maybe machines could very much, even at present, be very helpful in automating that process. And gosh knows that it needs help, because a lot of instructions and manuals are very poorly written. Well, let me give you an example of where this process is well advanced, and it's kind of art, though people usually don't think about it that way. Which is games like chess and Go, where people cultivate expertise and have styles, and so they produce beautiful products. Sometimes the best games are really a joy to go through. But now, computers are better than humans at chess. They're just better in the sense of being able to win. And Go also. However, that doesn't mean that that those things are no longer of interest to humans. On the contrary, some new principles have come up in studying what the computers produce, and you can do collaborations between human and machines that produce a better product than humans could produce alone, and things that bring more joy. So that's a kind of model. It's not a perfect model, because chess and Go are limited domains with rules that are very precise, and so art is much more open-ended. But that only makes the case stronger that man-machine collaborations could be very, very fruitful. And I don't think the right attitude for an artist is to put down the machines. It's to welcome new collaborators.
Yeah. So I feel like there's also a deep fundamental difference in that. With chess and Go, there's a winner. There's a very, kind of difficult to describe, but there is a very clear kind of objective utility function.
That's right.
Whereas with art, you can't really have this book wins.
Well, you could have people vote on which is well, in a way, that's a special case of the general problem of machine learning, which is you have to say what the goal is, and in supervised learning, you explicitly say this is a cat, this is not a cat, or whatever. So you make it into something that has a definite goal, and the whole art was in figuring out, or it's still developing, figuring out what the goals should be. There's a certain amount of arbitrariness in that, so it's not a rule-based game.
Right.
And is a three-legged feline a cat? Is a puma a cat? I don't know. You have to, or is an ostrich a bird? I don't. It's a pterodactyl a bird. I don't know. But you, but you could it would be arbitrary, but you could set parameters. You could propose artistic objects to an audience and have them vote on which ones they like. And in fact, something like, that's a parody, but I think something like that will have to be part of the process of having machines produce artistic products. They will have to, at least at first, until there's an audience of AIs, they will have to somehow get into the mindset of what an audience will appreciate. That's the criterion, right?
Do you have any idea what an objective scaling of art would look like?
Well, you put things up for auction and see how much they fetch.
Going into the free parameters of that AI that has learned what is going for higher, what is going for lower. Do you think that there would be any kind of variable that would be in there? Any kind of knob that you could turn to make your art objectively better, or kind of manipulate that?
Okay, I'm not sure I understand the question, but the great thing about neural nets is that if you just give them labeled data, right, they figure out what the underlying parameters is. That's a caricature, but that's the basic structure of it. So now a more profound question, which may be what you're getting at, is should the audience, in the case of art, should it really be left to the audience? And which audience? Right. Now, for instance, very specifically, for instance, I think many of us would agree that there was an efflorescence of particularly beautiful and lasting music in coming out of Vienna and that culture around 1800, a little bit before and a little bit after, and then earlier with some of the church music and Bach in particular earlier. And that was made for a very particular audience, an audience of aristocrats, amateur musicians who played the stuff and had a very sophisticated understanding of music. Whereas today, the audience for music is very different, and certainly if you look at what's commercially most successful,
it's no longer Bach.
It's no longer Bach, and okay. I know this is politically incorrect to say, but it's just not as good. It's just it doesn't go as deep. It doesn't stand up to scrutiny. There are different layers. You can't go. You can't. The more you engage it, whereas with the classical music, the more you engage it, the more you find, and with popular music, it tends to be just the opposite. It gets exhausted if you. So having the right audience can be very helpful, but it doesn't have to mean you could have different kinds of artistic products for different audiences. That's and you can objectify that some class of audience rates this higher than that, but you can't really compare.
There's no general intelligence for all music.
Well, you can't really compare. You can't say, well, this audience is better than that audience, even though I just did.
Well, you said the music, you didn't say the audience.
But they're both legitimate. They're both answers to legitimate questions, and give joy to people. So what more can you ask? Right.
So speaking on different audiences, I know that you live near Walden Pond, and something that you're proud of. Did you read Thoreau at all? I'm not sure.
I've read Thoreau a little bit in high school, and occasionally, because we're embedded in Concord now, I read, and I've enjoyed some of the writings that I've read, but I haven't felt the need to get really deeply engaged.
Yeah. Okay. Yeah, I was just curious. I know personally, I was never a huge fan of some of the transcendentalists, so I was curious if you had a polarizing opinion on any of them.
I should be very careful about what I say in view of where I live, and some members of my family revere these people. I appreciate, but don't revere, I would say, the transcendental movement was a remarkable thing for its time, and there are some striking phrases that came out of it and striking insights. So, yeah, it's nice.
Yeah.
But, to me, it's not a complete way of life.
I know Walt Whitman's Learned Astronomer gets talked about a lot, and often to my frustration. But
well, I like Walt Whitman a lot, actually. But again, as with anything, really, you don't necessarily have to accept everything to accept anything, right?
Right. Yeah. There's always good pieces in every rough. But so you mentioned your family. How's your family kind of impacted your life, your career? What's it like trying to have children and be on so many different groups?
This could be a very, very long discussion or very short. without soliciting their permission, I don't want to go into
Of course.
any kind of personal details. Just to say, my present family has been a joy to me and a source of strength in everything I do. Going historically, of course, I was very fortunate in my choice of parents. They were very, very supportive. They were not highly educated themselves, but had enormous aspirations for me. And my father, although he was not highly educated, his whole life was learning more, and I could see that. And then it's not family as such, but the society I was embedded in was kind of in Queens and New York City was a society of strivers. Most of the families were first or second generation in the United States, and it was astonishing in retrospect, especially in view of what's happening in the political scene now, that the attitude wasn't resentment, but aspiration. That we certainly didn't think of academics or scientists as hoity-toity, anti-populist people who are looking down our nose at them. I want to be like those guys. That's a very different and much more appropriate and constructive attitude. And that's definitely the attitude that I was brought up in, thankfully.
So, with the length of your career and the different achievements that you have, you could be in so many different places. Why here at MIT, and why doing what you're doing now?
Well, they're a family. Well, MIT is a great university, and they made me a fine offer, and they've been very, very supportive. There aren't that many. There are very few institutions at the same kind of level in science. I came from Princeton, which is at the same level, and earlier than that. Well, I've been at a very high level for a long time. So I did have choices, but the MIT is particularly. I find it particularly sympathetic because it's embedded in a city, in an urban environment. I like that. I'm a city boy, and it has a very diverse kind of population, and it's also highly rooted in engineering. All those things I like. Mm-hmm. But the main reasons, frankly, were personal. My wife's family is from New England, and they needed support at some stage, and my daughters went to school at Harvard and MIT, and they drew us in here. So that sort of thing. It was not. So it was largely personal, and we've really enjoyed living in New England, in Cambridge originally, and now here in Concord. So and we have a summer place in New Hampshire. So we put down roots here in a way that it could have been other places, but this is quite a good one. And I guess there's a process of spontaneous symmetry breaking, and this is where we happen to land. It could have been different. Yeah.
Okay. Well, thank you very much. This has been a great conversation. I'm very happy to have you on. Thanks for taking the time to meet with us.
Sure. Thank you. It's been a pleasure.
Yeah.